So we have Pythagorean fuzzy topological spaces. You should be aware of the fact that this video is almost entirely based on the seminal paper by Olgun, Unver and Yardimci from Turkey. But some other papers mentioned in the bibliography were important too. As for the idea of Pythagorean fuzzy sets as such, it comes from Ronald Yager, a renowned mathematician from USA who is very active in the field of fuzzy sets and other sets and logics that are used to measure and to investigate uncertainty phenomenon. These sets have been already generalized. For example, we have Fermatian fuzzy sets, we have n-Pythagorean fuzzy sets introduced by Mrs. Breniarska from Poland. Moreover, we have Pythagorean neutrazophic fuzzy sets too. Basically, the idea is similar to the initial concept presented by Atanasov nearly approximately 40 years ago, that we have a non-empty universe and we have two functions: membership, me, and new non-membership. Or you can think that they are like truth and falsity, and they both have values in interval 0, 1. But then suppose that, well, the sum of mu and ni can be bigger than 1, but the sum of their squares, as it's written here, is not bigger than 1, is lesser than or equal to 1. Alternatively, you could say that when you sum up the squares of these two logical values, then you obtain some r square of x, which is called the strand of commitment, or squared strand of commitment. Basically, the idea is that instead of mu plus ni equal to not bigger than 1, you have the same for squares. So it's possible that you have some kind of paraconsistency, I would say. And the degree of hesitation margin, is defined as you can see here, as the square root of 1 minus this squared minus that squared. Okay. All the operations are defined in a very standard manner, just like in case of intuitionistic fuzzy sets. So in case of complement, membership and non-membership are reversed. As for the intersection, it's calculated as minimum of memberships and maximum of non-memberships, and in case of union, we have max-min, as always. As for the inclusion, A is contained in B if and only if for every, by default we should assume that for every x in our universe, mu is not bigger than, mu A is not bigger than mu B, lesser than or equal to, while in this case non-membership of A is greater than or equal to the non-membership of B. As for the universal set, it's like here for every x, of course, that we have full membership and 0 non-membership, and as for the empty set, we have 0, 1, obviously. As always, we can define we can define topological space in this framework. So obviously we assume that the whole universe and the empty set are open, and we have closure under at least finite intersections, and under arbitrary unions, as it's written here. So in this way we obtain Pythagorean fuzzy topological space, and an example is here. You can analyze this example. We have 1, 0, so universal and the empty set. Then we have 5 other sets which are defined here. Our universe consists of 2 elements, 1 and 2. So for example, you have A1, membership of the element 1, it's 0.5. Non-membership is 0.7. But from the A2 point of view, you get 0.6 and 0.5. For example, we performed several calculations here. These are my own calculations. They are not complicated. Think about x equal to 1 and think about Pythagorean fuzzy sets A2 and A3. So we see that indeed in case of A2, for example, if we add membership and non-membership of 1, we get 0.6 plus 0.5, which is 1.1, which is bigger than 1. So from the Atanasov points of view, it's not allowed. But if you add squared values, you get only 0.61, so everything is okay from the point of view that is typical for Pythagorean sets. We can continue these calculations to ensure ourselves that both A2 and A3 are properly defined Pythagorean fuzzy sets. Here I calculated their intersection, A2 and A3. Okay, you can see using minimum and maximum functions, and in fact it seems that the resulting set is just C. Well, in fact you can check that A3 is contained in that the resulting set C is just A3, and you can check that A3 is contained in A2, so as we could expect, the intersection of A2 and A3 returns exactly A3. Of course, it doesn't prove that the family visible here is closed under finite intersection, but of course you can check other cases too, and then for unions. As for the neighborhoods, they are defined in terms of subsets, not something like Pythagorean fuzzy points, but of course you could. Or maybe they are already defined, you could define them, but in terms of subsets. So U is said to be a neighborhood of A if there exists an open Pythagorean fuzzy subset E such that A is contained in E and E is contained in this open U. In U, and what is open is E. It belongs to our topology. Okay, one can prove that A is open if and only if it contains a neighborhood of each of its subsets. It should be written properly. As for the image and pre-image, they are defined in the following way. There's two slides. Think about image. You have just a function from x to y, and the image of A with respect to f is defined by means of the following membership functions. You see supremum of all the elements that belong to the pre-image of y in y, and you take in fact supremum of memberships and infimum of non-memberships. As for the pre-image, we have this relationship and that one for non-membership. And the authors prove that the resulting objects are indeed Pythagorean fuzzy sets. There are many properties that are true, as you can see here. Okay, they are very typical and standard, and it's not very astonishing facts that they are true in this framework too. Moreover, you can think about all the properties, all the notions like interior and closure, and you can reconstruct other basic topological notions in this framework. But in this video, in this particular video, that's all for today. And this is the bibliography. This is this seminal paper on Pythagorean fuzzy topological spaces. But as you can see, there are even such strange things like Pythagorean M-polar interval valued fuzzy nitrosophic topology. And here you have a very general paper about the n-Pythagorean fuzzy sets. Thank you very much.